friends, today we are going to discuss how to find the specific heat of a polytropic process, of course followed by an ideal gas. A polytropic process is the one which follows the equation PV raised to n is equal to constant, where n can be any real number, it need not be an integer. For example, when we talk about an adiabatic process, PV raised to gamma equal to constant, where gamma is the ratio of Cp to Cv, that is also a polytropic process. Please note that a polytropic process, in addition to PV raised to n equal to constant, also follows the ideal gas equation. So if you are talking about 1 mole of a gas, the ideal gas equation becomes PV equal to RT. Using these two equations, we are going to find, number one, the work done in this process, work done in the polytropic process. We will derive a formula for that, and we will also find out the specific heat of the entire polytropic process. So let us proceed first with what we are supposed to find. So let us first proceed with what we are supposed to find. In order to find the work done and relationship between specific heat and work done, we must use the mathematical statement of First Law of Thermodynamics. That is, suppose dQ is the heat supplied to the system, du is the change in the internal energy, and dW is the work done by the system, then the total heat supplied is utilized in changing the internal energy plus doing the work. There are different sign conventions for work done, but here we are going to use the sign convention that work done by the system is positive. That is, when the system expands, the work is positive. So dW can be written as P into dV. Now this equation can be easily derived, and this is applicable to any process. Suppose the pressure of the surrounding is P and pressure of the system is also P, then the system is in equilibrium. But if we increase the system pressure to a little bit extent, say if we make it P plus dP, or if we increase the surrounding pressure, say, and make it P plus dP, then there will be work done by the system, right? So the work done by the system will be given by integral of P into dV. Actually, it can be work of expansion can be written as P plus dP into dV, which is given by P dV plus dP dV. But dP and dV are both differential terms and they are extremely small, so their product can be neglected. It can be almost taken as 0. So we can say that the work done is P dV in any process. Now our aim is to find this work done. Our aim is to find the integral of P dV. If you take specific heat of the entire system as C, please note I am not taking it as Cp. I am not saying that it is happening at constant pressure. I am taking it as C. Then dQ will be given by C dt. du will be given by Cv dt plus work done will be given by P dV. If you want to integrate both the sides, you will get C dt is equal to integral of Cv dt plus integral of P dV. So C dt and Cv dt are very obvious because we are changing the temperature from T1 to T2 here. So what is the challenge here? The challenge here is to convert dV also in terms of dt. So let me write this equation separately, which we are going to use afterwards. That is integral of C dt is integral of Cv dt plus integral of P dV. Now let us use the equation of the polytropic process and try to find the relationship between dV and dt. I am going to take the derivative applying the UV rule of derivatives. P as it is. Derivative of v raised to n is n v raised to n minus 1 dV plus v raised to n as it is. Derivative of p is dp, and as k is constant, its derivative is 0. This is equation number 1. Let us mark it as equation number 1. In addition to this equation, we also have ideal gas equation for 1 mole as PV equal to RT. If you differentiate this, I will get PdV plus VdP equal to RT. So let me now try to find the value of dP in terms of dV. So I will keep dP on this side. I get VdP is equal to RdT minus PdV upon V, and transfer V on the other side. If I substitute it over here, see what do I get? P n V raised to n minus 1 dV plus V raised to n into RdT minus PdV upon V equal to 0. Take a good look at this. V raised to n upon V will also become V raised to n minus 1. So what do I get here? It's P into n into dV into V raised to n minus 1 plus V raised to n minus 1 into R dt minus P dV equal to 0. I can cancel V raised to n minus 1 on both the sides. I can divide by V raised to n minus 1. This will get cancelled, and I will get n times P dV plus R dt minus P dV is equal to 0. That gives me n minus 1 times P dV equal to minus half dt. That is P dV is equal to minus R dt upon n minus 1. Now please remember the equation which we have written on the side. I am going to substitute P dV in this equation, and let us see what we get. We get integral of C dt from temperature T1 to T2 equal to integral of Cv dt from temperature T1 to T2 plus, instead of P dV I am writing minus R dt upon n minus 1 again from the temperature range of T1 to T2. C, Cv and R are constants. N minus 1 is also a constant that can be taken outside the integral sign. If we do that, then let us see the equation that we get. What we will get is C, integration of dt is T from T1 to T2 equal to Cv, integration of T is T from T1 to T2 minus R upon n minus 1, integration of dt is again T from T1 to T2. This gives me C into T2 minus T1 equal to Cv into T2 minus T1 minus R upon n minus 1 T2 minus T1. T2 minus T1 will cancel, and you will get the final answer as C equal to Cv minus R upon n minus 1. This is the formula for a general specific heat of a polytropic process. C is equal to Cv minus R upon n minus 1. Now, I also mentioned that we will find the formula for work done. The formula for work done is nothing but P dV, which is this part. So, this part here will give us the formula for work done. So if we write the work done dW as integral of P dV, it is minus R upon n minus 1 into T2 minus T1. This is the formula for work done. Please note that in the polytropic process we are getting the answer negative because the term T2 minus T1 will have its effect on volume. This work turns out to be negative. So if temperature T2 is more than T1, the work done will be negative because as temperature will increase, the volume will decrease, and therefore the work will be done on the system. That is why we have the formula W equal to minus R upon n minus 1 into T2 minus T1. This is with the sign convention that work done by the system is positive. If we are talking about n moles, you can simply add here n and you get the formula for work done as minus R upon n minus 1 T2 minus T1. Now there is a confusion between n and number of moles, so let me take number of moles as m. Then we have the formula for work done as minus mR upon n minus 1 into T2 minus T1. Please note this formula is also applicable to an adiabatic process where the work done will be minus mR upon gamma minus 1 into T2 minus T1. Please note when we are using the negative sign, we are using the first law of thermodynamics as dQ equal to du plus W. It is very important because in chemistry or in some other, according to new IUPAC conventions, this W is written as minus W. But let us not do that. Let us just apply the first law of thermodynamics in terms of conservation of energy. Whatever is the heat supplied is utilized in changing the internal energy plus doing the work by the system. So we have obtained two relations. One is the specific heat of the system and the second is the work done by the system. Both of them for polytropic processes, that is PV raised to n is equal to constant. Thank you very much.